Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello everyone, so I'm Yin Zhang from UT Austin. Today I'm going to talk about experimental design for practical network diagnosis. This is joint work with my student Han Song and Lily Q and UT Austin. Ideally, for network diagnosis, in an ideal world, you want every network element to be self-monitoring and self-reporting and diagnosing. And there is no silent failures, and basically everything will tell you. Also, you would like to have some kind of oracle that can simply walk through the haystack of data, accurately pinpoint all the root causes, and then suggest response actions. But of course, in reality, this is really difficult to happen. Okay, in practice, you have finite resources in terms of CPU, bandwidth, human cycles, money. Yesterday we hear that typically in campus network and enterprise networks, these resources tend to favor one-time instrumentation. Okay. Also, the decentralized and autonomous nature of the internet simply says it's infeasible to instrument monitor every organization. Even though we have here several talks about how centralization can help, but once you get to the boundary of different administrative domains, centralization becomes difficult. Finally, the protocol layering is universal in networking. And it's very useful and try to minimize information exposure. On the other hand, for management, it also make things a lot more difficult in that it's very difficult to obtain complete information at every protocol layer. The net result of all these factors is that for practical network diagnosis, it's really important to maximize the diagnosis accuracy under given resource constraints and information availability. And this is a problem what we term as a design of experiments. Okay. Basically, the input for design of experiments is, for example, you can have a candidate set of experiments that you can conduct. And I will give more concrete examples about what design of experiments will mean in different instantiations. And the candidate set essentially reflects the infrastructure constraint. For example, when you want to place a wireless sniffer, maybe in some offices, the owner will simply is not willing to put something close to them. You also, another input is information availability, which may include the existing information about the network that's already available to you. Also, it may include the information provided by each new diagnosis experiment. The third input will be resource constraint, which could be in the form of the number of experiments to conduct per hour, or the number of monitors that's totally available. Okay. The output of design of experiment is a diagnosis experimental plan, which include a subset of experiments to conduct, as well as a configuration of various control parameters, such as frequency, duration, sampling ratio. So this is a very abstract definition of the problem, and it actually has many different instantiations. The first simple example is networks of performance monitoring or benchmarking. Okay. When you have a physical network, it can support thousands of virtual private networks or virtualized networks, as Dinesh has talked about today. And what you would really want is that for each virtual network, you want to summarize a total network performance, which could be in the form of, for example, the traffic weighted average of individual virtual path performance. Like what's the average path delay or path loss rate or jitter over this virtual network. And Similar problem arises for monitoring. For example, you want to provide monitoring in some kind of average metric of the per application performance, or maybe so per customer performance. Okay. Now the challenge here is that it's actually very difficult to monitor all these individual virtual paths. This is simply the result of the fact that n-squared explosion. When you have n nodes, there are n-squared paths across them. This combined with the fact that you can have thousands of virtual networks, so it simply makes sort of monitoring overhead too high. The solution that's quite natural is that why don't we just try to monitor a subset of the virtual path and then infer the performance of the rest. Okay. And we can then sort of compute the sort of average performance across all these different paths. Now, this immediately gives us a design problem, which is which subset of virtual paths to monitor. As another concrete example, yesterday, one sort of a proposal for the discussion is this client-based diagnosis. What you can imagine that you have a bunch of clients that will, continuously probe each other, and then can use some kind of inference to localize trouble spot whenever a subset of clients experience performance problem. The trouble spot could be in the form of, for example, links or regions with high loss rate or high delay jitter, etc. The challenge is, again, this kind of probing approach will work if you have a relatively small number of clients, and like in the case of resilient overlay networks. But if you have more than, say, a few hundred clients, pairwise probing simply becomes too expensive. The solution is, again, can we actually monitor a subset of paths and infer the link performance? And whenever the end-to-end performance has some trouble, then you can infer, localize which links or regions are causing the problem. The design problem here is, again, which subset of paths to probe. We have actually also seen several similar examples through our talks and presentations yesterday. For example, David mentioned about this wireless sniffer placement problem. Okay, you have a set of offices or locations to place all these wireless sniffers, and as another input could be the monitoring quality and difference of the candidate location, which could be in the form of such as the probabilities for capturing certain the packets from different APs. Now, given this input and probably the expected workload at different APs and the locations of existing sniffers, the output will be k additional locations to placing wireless sniffers. Okay. It's again a design problem that tries to come up with a plan given resource constraints and information availability. In yesterday's poster, there is a one on how to do cross-layer diagnosis. Basically, you could potentially try to infer layer 2 properties based on probing the layer 3 path performance. Again, the question will be, which subset of layer 3 path to probe? This is a problem that keeps coming up, and it goes way beyond networking. Okay, but in CS there's software debugging, okay, or testing. Okay, you have a problem of select a given number of tests to maximize the coverage of corner cases. In car crash test, can we crash a given number of cars to find the maximum number of defects? Or in medicine design, okay, we would like to conduct a given number of tests to maximize the chance of finding an effective ingredient, and many more. Okay. Oops. Given that, there are so many problems that keeps just coming up. Okay, a natural question is there a way of having a unified framework that can solve all these problems at the same time, as opposed to keep coming up with ad hoc solutions for individual problems? Okay, and if we were to design such a framework, there are several key requirements in the context of network monitoring and diagnosis. First one is scalability. Okay, clearly we want the tool to work for large networks with, for example, 10,000 nodes or network elements. Okay. Another very important requirement is that it needs to be really flexible and to accommodate different application requirements. I mean, here we basically listed 3 requirements that we focus on in our initial design of the framework. The first one is something we call differentiated design. Okay, I mean, your framework you would like to monitor a number of interesting quantities, and different quantities may have different importance. For example, if I'm a service provider, maybe I would like to spend more resources on the substantive path that belong to our gold customer. And there is a second requirement is something we call augmented design. Just like in the example of wireless sniffer placement, you may already have placed a few sniffers in the past. Can the additional sniffers take advantage of these existing sniffers? Or sometimes when you conduct these experiments, some of the existing experiments may fail. Then you face the problem of can we conduct some additional experiments that can take advantage of these existing observations. The third one is multi-user design. Okay. Basically what happens is that we want this framework to support multiple applications and multiple users. And different users may be interested in completely different parts of the network or may have different objective functions. Just like in the network benchmarking example, the different VPNs may have different performance metrics. And we have made a baby step towards such a framework. And we have an upcoming paper in ACM Sigmetrics 2006 on something we call NetQuest. Okay. It achieves both scalability and flexibility by combining 2 key techniques. One is something we call Bayesian experimental design. We'll explain what it means in the next few slides. The second component is statistical inference. Okay. And for this specific framework, we developed it in the context of end-to-end performance monitoring. But it seems that it's very easy to extend it to other network monitoring and diagnosis problems. I will just try to give you a little bit detail about how this framework works. Okay. First of all, let's see what we want. Okay. I mean, given network, okay, we want a function of the link performance. For example, here we will use a linear function of the link performance. Here, x is a vector of the link performance, such as a link loss rate or link delay. Okay, and f is some objective metrics. As a simple example, you may be interested in the average link delay, or you may be interested in average end-to-end path delay, or you may be interested in all the individual end-to-end path delays. And this framework captures all, it's applicable to any additive performance metrics. But it seems that in our current work, we are trying to extend it beyond these additive metrics. What we can measure in this simple network is end-to-end performance, because it may be difficult to directly instrument or each individual link to monitor their performance. And the network performance monitoring estimation problem is that the goal is to obtain end-to-end performance on some path, which is fx. Then the design of experiments basically needs to select a subset of paths as to probe, such that we can estimate this objective fx based on the observed performance on these selected subset of paths. And there is a network inference component in the framework, which is given end-to-end performance, we need to infer the link performance, which is x.
I have a question for you. So as I understand it, you're saying that if you can probe it this way and that way, you can deduce the things. But that seems to be vulnerable to noise. Right? If you're doing that process at different times, the matrix may not converge.
That will be addressed by the network inference component. Because the inference it will explicitly sort of take noise into account. It has a noise component there. So, there is a slide on this. Mm-hmm. So the design of experiments, actually, let me just move into the Bayesian experimental design. The Bayesian experimental design basically says a good design tries to maximize the expected utility under the optimal inference algorithm. And by defining different types of utility functions, you can obtain different design criteria. Okay. So for example, if you try to minimize a squared error, where fx minus fxs is essentially the estimation error between the real objective and the estimate objective. Then you get something we will call the Bayesian A optimality. Then similarly, if you use try to maximize the expected gain in channel information, then you get something called Bayesian D optimality. I have 0 minutes. I will try to finish it as soon as possible. Okay. Once you have a design criteria, you can then apply a search algorithm trying to find an optimal design. And the framework is very flexible in that it can support differentiated design, augmented design, and multi-user design. And to address a question, okay, the inference components if you want to infer the real value x from some noisy observation y, what you typically do is that you are going to do using some technique called regularization. Okay, so which basically try to find x that that try to satisfy the constraint as much as possible. In the meantime, you are going to impose some structure on this noise component. And we have evaluated this framework using both Planet Lab experiments, also simulated topologies, and basically the results says everything just worked great. And so if you are interested in figuring out how great it is, then please read our Sigmetrics paper. Okay. The summary of this work is basically we bring Bayesian experimental design into network measurement and diagnosis. And we believe having such a flexible framework to address a wide class of design problems is a very useful thing. Okay. And we have experimentally shown its effectiveness. In the future work, we plan to address other aspects of the design, such as making the measurement designs fault tolerant, or applying our technique to other problems, or extend our framework to incorporate additional design constraints. Okay?
2 questions.
Uh-huh.
So but I thought vertex cover was empty. Would
Yeah.
that mean that your optimal...
Tom, you need to speak louder.
Sorry, okay. So isn't it the case that your optimality definition requires you to solve MD?
Yes. Basically, the problem of finding optimals of the design. Yeah, I said that. Any other question?
Okay.
Okay.
That's